Let's turn to actually computing the regression line in a particular case. Here's a picture of the scatter plot of the Galton height data. We've got the scattered dots here in blue. We've got our nearest neighbor's prediction line in gold. And then we've got this black line, which is fairly faint, and it's the line of best fit. We've used the fit underscore line equals true option in the scatter command in order to produce that line. The line of best fit in this case is awfully close to the predictor function that we constructed. The line of best fit is better in many ways. It's a straight line, it really is a straight line. We can compute and interpret its slope and intercept, and it has a lot more statistical theory to back it up. But I want us to think a little bit more about how we could compute that line of best fit. In the last video, we saw some formulas. Let's explore those formulas a little bit more. Let's try a little thought experiment. Suppose we're searching for the line of best fit and we don't know those formulas from the last video. We do know the form of the line of best fit. The equation is going to be y equals mx plus b, and we just don't know what those m and b numbers are. Well, if you give me m and b, I can draw the line and I can try to measure how good a line have you given me? What's the fit, so to speak? And here's one way we could measure the fit. In this displayed equation in the middle here, we see that we're defining the fit to be m times the x-coordinate of a point plus b minus the y-coordinate of the same point, and we square that. And then we sum those quantities up over the all the points in the data set. Notice that mxi plus b, that expression is actually our predicted y value. So we're taking the predicted y value, subtracting off the actual y value, and getting the error, and we're squaring that error and adding up all those squared errors. That should give us a positive number, which measures the fit. If the number is low, we've got a very low collection of errors and we have a good fit. And if the number is high, then we have a kind of bad fit. So we'd like to minimize this quantity, right? We probably can't get it to be zero, this fit, but we'd like to minimize it all the same. Think for a minute about fit. It's a function of m and b, those unknown numbers. And of course, it's also impacted by all the points in our data set, which we happen to know, they're actual numbers. So m and b are the only variables here. And so fit is a function of two variables, m and b. Not only is it a function of two variables, it's a quadratic or degree 2 function of those variables, right? M can only get squared and b can get squared, and we could have some cross terms like m times b, but we get at most a degree 2 polynomial in the m and b's here. So fit is a degree 2 function of m and b, and we know how to find the minimum of a function of two variables from SM223 or maybe SM221 when you took those classes at the Naval Academy. You would take the partial derivatives of this function with respect to each of the variables and set those partial derivatives equal to 0 and solve. And that would give you your critical points, right? And here, when you take the partial derivatives of a degree 2 polynomial, what you get is a degree 1 polynomial. So we've got a degree 1 polynomial in the m and the b. It looks something kind of like this. A number times m plus a number times b plus some other number. Okay, and that might be the form of the m derivative, and it's also the form of the b derivative. And when we set those guys equal to 0, we get a linear system of equations, two equations in two unknowns, and those are linear equations, and we can solve those equations to find m and b. And that's how we found the equations that we gave you in the previous video. You might be wondering why we're certain that we're getting a minimum value for the fit, but that comes about because of the interpretation of the fit function as sums of squared errors. And we can see that we're never going to be able to maximize that. We can always take worse and worse lines, but we could minimize those things. And so this gives rise to the minimum. There's one situation where we don't actually get a minimum. We don't get a unique line of best fit, and that's if all of the points in our data set are all the same point. In that case, you get that all lines through that data point have fit equal to 0, and so we don't get a unique line of best fit. That exception doesn't really arise in practice. Okay, that's the end of the thought experiment. Let's find the slope and intercept in terms of the correlation coefficient. And here in this code cell, I've defined a number of functions. We've already encountered the standard units function and the correlation function, but now we're defining the slope function. It takes a table and an X label and a Y label and computes the correlation, the standard deviation of X and the standard deviation of Y, and it returns the slope of the regression line for Y regressed on X. And similarly, we have the intercept function, which is returning the intercept of Y on X, where the data is contained in this table. So let's apply these functions to the Galton data and find the slope and intercept of the line of best fit there. And when you do that, you find that we can use the slope and intercept commands and print out what we get. And we see that the slope is about 0.63 and that the intercept is about 22. And why do we care about those numbers? Well, first, they're kind of interesting numbers that tell us something about how the heights of children and parents are related, but also they help us predict the heights of children. So here's a parent-child combo with their heights, and to predict the child's height, we take the slope, 0.63, and we multiply by the mid-parent height, which is our x-coordinate, we add the y-intercept, and then we get this number, which is just below 67 inches, and that would be our prediction of the height of the child. In fact, our prediction is pretty far off here. The child was actually 71.5 inches. And hey, predicting's hard. It's not so easy to predict well. The average neighbor prediction was even a little worse. If you look at the average neighbor prediction, they were even further off than ours. Okay, we can add the regression prediction to the table, and that's what we get here. And then we can draw a scatter plot of the nearest neighbor prediction, that kind of wending, waving gold line, and the also the line of best fit here in light blue.